So this is the topic we are going to learn about today, and we are going to learn about it strictly in the context of convolutional neural networks. Now, before proceeding, let me ask a question to all of you. Let's keep this interactive, and I would like everybody to participate. Okay, just a simple question. Imagine I have an artificial neural network. The architecture doesn't matter. Let's say we have 3 layers or something, and I have trained it on a data set. Now, let's say I have another data set related to images. The first one was also related to images. And the resolution of images is different here. Let's say here I was having 100 by 100 images, and here I am having 200 by 200 images. So is it possible for me to reuse this ANN on this data set? Or if you can answer by a simple yes or no. Think about it. I am going to train an ANN, or let's say I have trained an ANN on a data set of images where images are 100 by 100 in resolution. Now, can I reuse this ANN to classify the same images, but their resolution is 200 by 200? Is it possible?
No, not possible.
Other candidates? Both the options are available, or if you can answer via chat also, and or via mic also. Okay, you have both the options. If you want to explain why or why not, you can also do that.
Because the number of nodes in the input layer will differ.
Number of nodes in input layer. No, not exactly correct. So the correct answer is no, we cannot. Who can explain why? Why we can't do that?
Means you are asking like uh, a simple ANN can be used for image data set. Is that?
No, the question is, so first question was, I have an ANN, I have trained it on this data set, and now I want to use it for making prediction on this data set. Okay, so the answer is no, we cannot reuse that. Now the next question is why? Why we can't do that? What is stopping us from applying this neural network on a data set with different shapes of images?
Is it because of the weights might change and the output will differ in both?
Correct. Weights of which layer?
The hidden layers,
No, the
input
input layer.
input layers. Sorry.
So very simple concept. If we talk about the weights of input layer, okay, let's say we have these neurons, n number of neurons, right? So how many weights do we have in this layer? What does it depend on in an artificial neural network? I talk about this neuron. So the number of weights in this neuron, what does it depend on?
Initially unknown, but later on we can reduce.
No. I think when you say reduce, you are referring to the loss, the error. I'm talking about weights. Like how many weights do we have here? What does it depend on?
It depends on the number of nodes present in the previous layer.
Adjacent layers.
Number of nodes present in the
Previous layer.
Previous or
correct.
next layer.
No, not previous, not next, only not adjacent. Okay, all of you should be very precise with your answers. Adjacent, not correct. Next and previous, also not correct. Only previous layer. Okay, number of weights we have in an artificial neural network layer, or we also call it fully connected layer. It only depends on the number of nodes in the previous layer. Okay, so I was talking about the first hidden layer, right? The input layer maybe. So we can say that the input layer this answer is also correct that the number of weights in this will depend on the previous layer. So as this is our first layer, what is the previous layer? Simply our input, the layer which is receiving the input. So we can say the number of weights of the first layer. Okay, first layer meaning the first hidden layer. Input layer is just an abstract if all of you are aware. So it simply depends upon the input layer, meaning it simply depends on the input. So if I have an input layer, sorry, if I have an input of an image which is 100 by 100, all of you are aware, you will have to convert it into a vector for a ANN. Yes or no? That is how ANNs receive input. You will have to convert it into a vector, and the shape of it will be 10,000 by 100 by 100. So the number of weights we have in this layer in each neuron depends on this number. This is the input we are receiving. You can assume this is your input layer. So the first layer we have in our neural network, or the first hidden layer we have, the number of weights in each neuron will depend on that input. So in this case, it is 10,000. Is this clear to everybody?
Yes.
Right. So now as we have established that the number of weights depend on the input. So if I train a neural network, now I can have other layers also, but those are not really affected much. Correct? So it depends on this input shape. So once I have trained an artificial neural network on this data set, okay, now the weights are according to that data set only. Correct? So if I want to reuse this for a data set which, let's say this data set was about object detection and we had mainly 3 objects. So let's say I have the same objects, same images, but only the resolution is different. Still, I cannot reuse this ANN to classify images present in this data set. Why? Because each neuron here in this layer has 10,000 weights. Correct? Now, for the weighted sum calculation, you will multiply 10,000 weights with 10,000 inputs. But in this case, you will have a different number of inputs. So it cannot be done. You may need a little bit of revision to understand it completely. But the simple fact is the number of weights directly depends on the input that an artificial neural network layer or fully connected layer is receiving. That is why it cannot be reused. Now, on the other hand, let us take the case of a CNN. So what do we have in CNNs? We have filters. Yes or no?
Yes.
Like here we have a layer of neurons. In case of CNNs, we have filters. Okay. So let's say I am using a 3 by 3 filter. Correct? So I have trained this CNN for a classification task on this data set. So this filter 3 into 3, that means total 9 weights are there. This filter has learned to extract the features in such a manner that the classification can be performed. So now can we use, and let's say we have total 16 such filters in the first layer of the CNN. Can I reuse the CNN on this data set? Yes or no? First question. We don't need to talk about the rest of the architecture. We only need to talk about the first layer. The answer is yes, we can reuse. How so? Let us understand with respect to simple filter. So the difference is here the filter is same 3 by 3. The filter or the weights inside this filter are not really dependent on the shape of input. Okay. Here, how many weights you have, that depends on the number of inputs. For example, if I have a 100 by 100 image, the 3 by 3 filter will slide accordingly. I hope all of you know when we perform the convolution operation based on the stride selected, mostly it is stride 1. So we will be sliding this filter over the whole image. Let's say this is my 100 by 100 image. So I will take this 3 by 3 filter and I will slide it over the whole image. So if you remember the formula, the output shape will be 98 by 98. Yes or no?
Yes.
Do all of you agree with this? And if I'm using 16 filters, it will be 98 by 98 by 16. Okay. Now let's say I have a bigger image, 200 by 200. So we can use the same filter, 3 by 3 filter. The only difference is now it will have more slides. So the output will be 198 by 198. So you see the output shape is changing, but in the architecture there is no difference. If you are using this CNN layer on a 100 by 100 input, it will produce this output, but it will work. If you are using this on this input 200 by 200, this will work. The output may be different, but that doesn't matter. The architecture is not directly getting affected by the input. So that is the difference between a CNN layer and an ANN layer. And that is why the CNN layers or a convolution part of a neural network can be reused if the problem is same. That's what we need to learn before we talk about transfer learning. How exactly it can be reused. So is this difference clear to all of you?
Can you reiterate the ANN part?
Okay. In case of ANNs, now in order to understand this, we need to remember the theory also. It's a very simple fact that when we talk about a layer in an artificial neural network, okay, the first hidden layer, the number of weights we have in each neuron, that depends on the number of inputs we are receiving. All of you agree with that?
Yes.
Correct. So let's say if I have a ANN and if I'm receiving 5 inputs, so each neuron in that layer, first hidden layer, will have 5 weights. If I am receiving an input, if I am receiving an image as the input, where the image is 100 by 100, so we convert it into a vector 10,000 by 1. So each neuron will receive 10,000 input. Now for weighted sum calculation, we will need 10,000 weights. So if I have trained a neural network on a data set where each image is 100 by 100, the weights in that layer will be 10,000. So now I cannot reuse it anywhere else. Clear now?
Yeah.
But in case of CNNs, we have filters. They do not directly depend on the shape of input. So all of you just, let's say if you are not able to recall the mathematics, because you need to know two things to understand this difference. You need to know how exactly weighted sum calculation is performed. You also need to know how exactly the convolution operation happens. Now, let's say you are not able to recall both of them for now, so you just need to remember one thing. In case of ANNs, the weights you have directly depends on the input. So in case of ANNs or fully connected layers, the weights you have, it directly depends on the input, right? In case of ANNs. But in case of a convolution layer, the weights do not depend directly on the input. Hence, we can reuse CNNs more often than ANNs. So now that we have understood this, let us talk about transfer learning. What is this concept of transfer learning? When all of you created your first CNN, okay, we have to understand the purpose first. That is my approach. First, we need to understand the purpose of what we are studying so that we can understand it better. So when all of you created your first CNN, was this confusion there that how many CNN layers we should use or how many convolution layers should be there? Okay. Second, what should be the filter size? Correct. And whether we should use padding after each layer or we should use padding after, let's say, 2, 3 convolution layers. So was this confusion there, or is this confusion still there? Let's say I give you a new task, a new data set. So I think all of us can agree that you will have these three questions. How many convolution layers I'm going to need to solve this problem? What should be the filter size for each layer? And whether I should add padding layer after each convolution layer, or I should add padding layer after, let's say, 2, 3 convolution layer. Do all of you agree with this?
Yes.
Other candidates?
Yes.
Okay. So in order to solve a problem, let's say machine learning problem, what we do is we experiment. So it is not the case that you will create a neural network, especially when the problems are a little bit tricky. It's not the case that you create one neural network, okay, you create one CNN and then you can get best results. No, you have to try different things. Okay, create a CNN which has, let's say, 2, 3 convolution layers. Then create your CNN2 by making some changes which has more convolution layers. Then maybe create a CNN which has like block structure, multiple convolution layers before a padding layer. Correct? And then a CNN layer, let's say, which is very huge in architecture. So you have to try a lot of things. You have to do a lot of experiment, and then you are able to finally create an architecture which can solve the problem effectively. For simple problems, this approach is okay. But when we have more and more difficult problems, then the experimentation we have to do, the number of things we try, that increases exponentially. Now, with that, the biggest problem is expertise. So, do we really have the expertise to fine tune or change our architecture as per the requirement? Maybe or may not be. Okay, let's say some of you are smart enough, they know exactly what to change. Maybe some of you don't know. So, expertise, let's say we have 50-50. Next constraint is time. Do we have the time to do this? Okay, to train so many architectures and then do the experiments? May or may not be. The biggest problem is resource. So when you have to train a neural network now, any kind of neural network, basically when you have to create a deep learning project, what all of you are using? I think Google Colab. Yes or no?
Yes.
Yes.
And why are we using Google Colab? Can anyone answer?
It
GPU.
is free.
Because of the GPU. Okay, for creating deep learning projects, we need the free GPU that the Google Colab provides, correct? The Kaggle kernel also provide that. So we need that free GPU, and using that we can train our neural networks. So I hope all of you are aware that it has a time limit, right? Let's say when you are doing something, you may receive a message, okay, you have run out of the time limit. It has I do not recall, it has maybe a daily or a weekly time limit, number of hours you can use those resources, correct? And when you will go to actual projects, then you will need more compute power. Only one GPU is not going to be sufficient. So we have these three constraints with respect to these experiments. Expertise, you may have, may not have. Okay, time, you may have, may not have. Resource is definitely a constraint for everybody. GPUs are expensive, even if you decide to purchase a cloud service. Okay, you purchase some good compute, it costs a lot. So because of these three problems, it is always not feasible to try this approach. That okay, we can experiment with our own neural network, we can try different layers, different combinations, and we keep on doing that to finally create a network which can solve the problem. Now, that is where the concept of transfer learning can help us. So those who have already covered this, can they tell me what is transfer learning exactly?
We're using the pre-trained models, which is already trained for a new problem. So we don't have to. It's not on our on our resource expenses. It is already trained. It's just that we are reusing the whole trained model for our new problem. So it saves us the resources to do the computations.
Correct. No, we have in most of the times we have to train it again, but the resources required in figuring out and doing a lot of experimentation are different. So absolutely correct answer. Transfer learning is about using already available architectures, using pre-trained architectures. So I hope all of you understood the purpose, that why is it not feasible to always follow this approach, do our own experiment. Correct? It is better to use an architecture which we know is already good enough. So a lot of researchers and let's say a lot of people from the industry, they have created, after a lot of research and after a lot of work, they have created sophisticated architectures, and we can use them to solve our own problems. And there are two ways we can do that. One way is, if our problem is exactly same, then we can use the architecture as it is without even training it. So let's say there is an architecture which is trained on object detection, so you can use it as it is if your problem and your input shape of images are exactly same. Second way is that you use an already available architecture, but you fine tune it a little bit. Okay, that you fine tune it a little bit to match your problem. For example, there exists a pre-trained architecture which has been created to work on 300 by 300 images, and it has, let's say, 100 classes, let's say 1000 classes. But you are dealing with a problem where you have only 200 by 200 input and let's say 10 classes. So you can change a few things in that architecture and then you can reuse it. So this is what transfer learning is. The purpose of transfer learning, why we need transfer learning, and what exactly is transfer learning. Is it clear to everybody? All of you need to give me an update on that so that we can start with the project.
Yes.
Okay, great. So this was just a rough discussion about what is transfer learning and why we need it. Now let us start our project. So obviously we will need Google Colab for this. So all of you open a new Google Colab notebook and do not forget to turn on the GPU. I hope all of you are aware, but just in case, in order to turn on the GPU, you need to click on runtime, change runtime type, and then you need to click on the GPU. All of you ready with the notebook, Colab notebook?
Just 2 minutes.
Ready now, all of you? Okay.
Yes.
This is going to be hands-on, but the first part where we import libraries, let me just copy paste that to save some time.
You can also paste in the chat if you don't.
Yes, yes. Okay. So first, let me introduce all of you with the data set. So here our main goal is to learn how we can use an already available neural network from keras.applications. Okay, so we are using the simplest data set that exists to understand that, which is CIFAR 10. This is a data set about classification, and here we have images belonging to 10 different classes, or let's say images of 10 different objects. Okay, all of that, what exactly are those? I will mention in a list. First of all, let us import our data. This data set, why we are using it? Because it is simply available in the keras.datasets API. So we don't have to do a lot of data related operations to use it. We can simply do data dot load and we will get our data set. Also, we will not need to split it. Those who are typing, make sure these X and Y's are capital. I will explain later why. So that's it. We have loaded our data. Now let me also provide all of you with a reference of what kind of classes do we have here. So we have okay. So these are 10 different types of images we have in this data set. We have images of airplanes, we have images of automobiles, bird, cat, deer, dog, frog, horse, ship, and truck. Okay, different types of images, and all of them have been labeled from 0 to 9. So total 10 classes. 0 for air, 0 represents airplane, 1 represents automobile, 2 represents bird, and then 3, 4, 5, 6, 7, 8, 9. Just like that, our labels exist. Let's say still you want to check, so we can apply on one of the labels, either white train or white test. So it will give us an idea of what exactly we have in our labels. So as you can see, you have values here from 0 to 9. So 0 in our label represents an airplane. That means if an image is labeled as 0, it is an image of an airplane. If you have an image labeled as 1, it is of an automobile. 2, bird, 3, cat, and just like that. Okay. I hope all of you can see this output. Now let us explore our data set a little bit. Here by training data, we mean the data set for training, which is our X train. Training labels Y train. Testing data X test, testing labels simply Y test. This will give us an idea of exactly what we are dealing with.
So one doubt.
Yes.
Is that Spartan class will automatically do the splitting like X and Y and X test Y test?
Just a second. Someone has asked me to share it again. Okay. Okay, I have shared everything again. Yes. What was the question?
The Spartan dot load data will it automatically split the data set like into train test, X test, Y test?
Yes. This
Okay.
function will provide the data in with the split itself.
Okay.
Okay, the dataset itself exists like that in the datasets API Cypher 10. Is load data is simply loading that. It's not like it is splitting. This is how it exists. It is simply loading it or it is giving back it to us.
Okay.
Got it?
Got it. Yes.
All the datasets or most of them that are available in the library itself, they are available in this format, already splitted.
One question here. The training data shape is 5,000 and testing is 10,000. So
15.
we have. Oh, I'm sorry, I read it right. Okay. Yeah, okay. So the split has happened. How then is it 80-20?
No, that doesn't matter. Here, 50,000 to 10,000, that is a format that is present. Like this is how it is present in this Cypher 10.
Okay,
There
so
are no
even if we
datasets
use
API.
train test split, it's gonna be split the same way, or
No, there we can control how we split it.
right? Okay,
How
okay,
much how many images, or let's say how much of the data you want for training, how much you want for testing. But here we are simply using what it is providing.
okay. So this is how it's by default available, right?
Yes, this is how it is available. If you want to change it, you obviously can change it. You can combine both of them and then decide on your own how much of the total 60,000 you want for training, how much you can do 40-20 maybe. It's up to you. It can be done.
Okay, okay. Thanks.
Let's say you want them to be 40-50. Okay, concatenate them and then do the splitting again.
We can concatenate it by using NumPy, right?
Yes,
Yeah. Okay, thanks.
because these are ND arrays.
Yeah, right.
As you can see, I'm able to use the shape attribute. It confirms the fact that these are ND arrays. These are available as ND arrays.
Right. Thanks.
Okay. Now, before proceeding, let me ask a question. Are all of you aware what exactly we have here, what we are dealing with? Like this is 50,000 by 32 by 32 by 3. So is it clear to all of you what exactly is this, what this represents?
50,000 images with 32 by 32 size of 3D RGB.
Correct, RGB. And let's say if it was 50,000 by 32 by 32 by 1, then
Black and white.
correct. So black and white or grayscale images have one, or they may not even have it. Let's say if you only have 32 by 32 or 32 by 32 by 1, it means we are dealing with grayscale images. We have 32 by 32 by 3, it means we are dealing with RGB images. Okay. So their corresponding labels, and 10,000 images for testing and their corresponding labels. Now, before proceeding, we would like to have a look at the images we are dealing with, correct? It is always a good idea to have a basic understanding of how exactly the images look like, okay, what is their complexity and what we are dealing with, because there is not much exploration when it comes to image related data, correct? All exploration that we need to do is just print some of the images to get an idea of what we are dealing with. So I hope all of you are aware with this technique. in order to print a lot of these images together, what we can do is we can create a figure, and inside that figure we can create a lot of subplots, and each subplot we can print an image, or let's say show an image. So let's do that. So let's say I want to print 200 images. I think they will be sufficient to get an idea. So I run a loop for 200. Now all I'm going to do is I'm going to create a subplot, and in each subplot I'm going to print an image. Okay, if all of you, I'm sure you may have done it. So can anyone tell me why I'm writing I plus 1 here?
It is basically range and which is going to be plus one incremental.
Correct. So here in the subplot function, we are giving the subplot number, or you can also say subplot ID, and that starts from 1. But our loop will start from 0. Our data set also starts from 0. When I say range 200, so we will be picking up 200 images having indexes 0 to 199. But in the subplot, the IDs have to be 1 to 200. That's why I plus 1. So when we have the first image present at index 0, the subplot ID is actually 1. When we have the second image present at index 1, the subplot ID is actually 2. Just like that. After that, when you print images, we definitely turn off the access. And then what function do we use to print an image?
I am sure.
I am sure. Have all of you used the function from the OpenCV library also? Using OpenCV library also, you can read images and print them.
Is that I am read, right? OpenCV.
Yes, I am read for reading, and then I think the I am show is same for
Yeah.
visualizing. So what this piece of code or this loop will do is it will print 200 images in a grid of 20 by 10. That means 20 horizontally and 10 vertically. So here we have 200 images from our data set. Now you may ask, sir, can we only print the first 200 images? No. Let's say you want to print any 200 images anywhere in between, so you can change the range. So if I write 1000 to 1200, then it will print those images. So that way you can check a lot of them. So here are our images. Okay. Next. So in this, I would also like to show you something called as train validation and test split. So let me first ask this if you have already done it. If you have done it, I will move quickly. If not, then I will explain. So when we create big projects, we actually have 3 splits. We have train, validation, and then we have the test split. Train and validation are used at the training time. So I hope all of you are aware when you train a neural network. So when it is being trained for each epoch, it does the training and testing both. So for that, we will use train and validation set. And then after that, we will again use a testing set. So is everybody aware of these 3 splits or no?
No, sir.
Okay. So if not, then let us understand them. So this is just a method of evaluation which makes sure that, okay, everything is working fine, right? Even better, we have cross validation. Let's not go there. So I hope you have studied that in machine learning. For now, let us focus on this. So for a lot of projects, it is fine if you just do train and test set and then you do it. Okay, at the time of training only, both will happen. But it is better to have three sets: train, validation, and test. So at the time of training, you will have train set and validation set, right? Both will work. And then once that training is complete, you make predictions and again do testing with a separate testing set. That is how it works. If you remember machine learning, there it was not the in machine learning projects, it was not the case that at the time of training only you are getting the training accuracy also for each epoch and then the testing or validation accuracy also. Correct? But in neural network it happens. So now we are taking one more step. Okay, what happens at the time of training? We will have that. But then, just like the old school method, we will make the predictions and then we will compare the predictions of the actual labels on the test set. Making sense to everyone?
Yes.
Okay. Now the question is from where we get this validation set, right? Right now we have the training set and we have the test set. And obviously in each set you have the train and X and Y, training data and labels. So what we can do is we can use the train set and we can split it into two parts: the training set and validation set. And we will keep the test set as it is for the final testing. So we will split the training set into two parts. Right now in the training set, we have 50,000. Yes, we have 50,000. So let's do a 80-20 split. So we will keep 40,000 for training and we will keep 10,000 for validation. Okay. And then in the test set, we obviously have 10,000 for testing. So on this, we will train our data set. And at the time of training itself, the model for each epoch will keep checking the performance on these 10,000. And once the whole training is complete, then again, we will check the performance on this separate test set. So this is what we are going to do today. So I hope it is making sense. Now let us simply split the training data into train and validation. So that way we will have train, val, and test, three sets. So remember I said initially that we need to keep them capital. Now I can have small. X train. X train is our training set. Images X val, testing set images. Y train training set labels. Y val validation set labels. And from where we will get this? From our original capital X train and capital Y train. Done. So here we had X train and Y train, 50,000 images, 10,000 and 50,000 labels. Now we have splitted them into 40 and 10. So 40,000 images, 40,000 labels, X train and Y train, 10,000 images, 10,000 labels, X val and Y val. Let us print all of that information just to be sure. Okay, before that, before we print the shapes again, let's do one more step. So I hope all of you are aware that whenever we have our data like this, right now the shape of the labels is 1 and 1. So can we provide this as input to our neural network, or we need to make any changes? If we are using the categorical cross entropy loss function. Simple question to all of you. Because this is related, this you may have done in ANNs also, CNNs also. The question is, if we are using the categorical cross entropy loss function or cost function, can I keep my data like this, or do I need to make any changes? The labels. Okay, you may want to note it down. The categorical cross entropy loss function that we use, it requires your labels to be one hot encoded. Okay, you may be wondering, sir, why do we need to make any changes? Why do we need any encoding if they are already available in numerical format? Okay, we need to do that because the categorical cross entropy cost function requires your labels to be one hot encoded. Then only it works. So you may have done this step already. Let's do that. Now, why did I run all? Because this statement was correct. So maybe this executed, this did not execute. So if I run this cell again, this will become 10 by 10. So that's why I had to execute everything again. Now I have not received any inputs. So let me ask this. Have all of you never used this piece of code? Have you never used this two categorical function in your previous multi-class classification projects? Doesn't matter whether it was CNN or ANN.
No.
No? Okay. So next question is, let's say you are creating a neural network for multi-class classification. Doesn't matter images or structured data, or let's say ANN or CNN. So what was the loss function you were using? Cost function. For example, if it is binary classification, you must be using binary cross entropy. If it is multi-class classification, then what did you use? You can check your previous notebooks also to confirm.
I think sigmoid. Sure.
The sigmoid is an activation function. It's not a
Oh,
loss
sorry. Yeah.
function.
It's an activation.
Sigmoid you will use in the output layer of a binary classification network. If it is a multi-class classification network, we will use softmax. I'm talking about the loss function. Like in case of binary classification, we use binary cross entropy. What did you use in multi-class classification projects? Check your notebooks.
Cross entropy.
Which one? Complete name.
Cross. Huh?
There are two: sparse categorical cross entropy, and there is categorical cross entropy. So which one did you use?
Not sure. I'm not sure. But I've not heard of the multi-cross entropy, but I've heard the sparse.
Okay.
Most of the times we have used binary cross entropy.
So have you created any multi-class classification project?
I'm checking.
No, we haven't.
Okay, but I think someone mentioned that you have done Cypher 10 already. Anyway, it's good if you have not done it. So let me give you a very important piece of information today. So normally what I share with the participants is this table. Let me show you that table.
Sorry, we have used categorical cross entropy as well.
Okay, so if you have used categorical,
Yeah,
can you show me your
I can
screen?
see. I can see that we have used this to categorical also.
Right. So just a second. Let me find out. You see this table, right? So if we have a regression task, then our loss function or cost function is mean squared error. If we have a binary classification task, then our loss function or cost function is binary cross entropy. Okay, so there we have no choices. We have to use these regression, this one, classification, this one. If we have multi-class classification, then we have a choice. So basically, two are available in TensorFlow, which we frequently use. You see, apart from these mean squared error, binary cross entropy, there are a lot of functions available. You can use custom functions also if you're using TensorFlow, but these are the ones that are used as a standard. So when it comes to multi-class classification, we have two of them. One is categorical cross entropy, and one is sparse categorical cross entropy. Okay, same thing basically. Categorical cross entropy and sparse categorical cross entropy. So we have two of these. This one, I mean, not always, but let's say in 7 out of 10 cases performs better. So we mostly use this one. So this one requires your labels to be one hot encoded. I hope all of you are aware what is one hot encoding, right? So let's say if my labels are already numerical, normally we do encoding, the confusion arises here. Let's say if we use encoding when we have our data or our labels in categorical. For example, you had airplane, frog, dog, cat, deer, just like that. And you need to encode that to a numerical format. But sir, why are we doing the encoding again if they are already present as 1, 0, 1, 2, 3 labels? That is because the categorical cross entropy requires your data to be one hot encoded. The sparse categorical cross entropy does not require. So if your loss function that you are using, if that was sparse categorical cross entropy, you will not need this one hot encoding step for which we are using the two categorical function. So difference between these two, clear to everybody?
No, can you repeat it?
Okay, let me repeat. When it comes to multi-class classification, for the loss function, we have two choices: categorical cross entropy and sparse categorical cross entropy. Categorical cross entropy loss function requires your labels to be one hot encoded. Simple. One hot encoded labels. The second one does not require your labels to be one hot encoded. You can, let's say if you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then you can use them as it is. So we are using that two categorical function to convert our labels to one hot encoded labels because we are going to use the categorical cross entropy loss function. That is why this step, two categorical. Clear now to everybody? Difference between these two, is it clear to everyone? Very important.
Yes.
Okay, if someone is having confusion, they can ask again, no problem. So we have created three different sets. We have also taken care of the encoding. Now, once again, let us check the shape to understand what we're dealing with and everything is correct or not. So we need to keep checking the shapes because the errors that you receive most often in these projects is shape mismatch errors. Errors like, okay, like 10,000 by 10 expected received 10,000 by 1, right? Or 40,000, sorry, 32 by 32 by 3 expected received 32 by 32 by 1. So these are the kind of errors you receive the most. Or let's say for 40,000 images, but only 30,000 labels. So these are the kinds of errors you run into. So it always makes sense to have these shapes checked frequently in order to avoid these errors. So even if you get the error, you can go back and check where exactly you had those errors. So let's do that. We need to print the shape of x train, y train, x test, y test, and x val, y val. Capital X train, capital Y train are your original training set where we had 50,000. After splitting, we have small. Testing remains same, capital. Okay, so here we can see all their shapes. Training data, we have 40,000 images. And training labels, we have 40,000 by 10 corresponding labels. Why? Because we have one hot encoded. Instead of 40,000 by 1, you see 40,000 by 10. So as there are 10 classes, there will be 10 dummy variable columns. Validation data, 10,000 images, 10,000 labels by 10. Testing data, 10,000 images, 10,000 labels. Now you may ask, sir, why we have not encoded the testing set? That is the reason why we have done this split, because the validation and training are going to be used while training with respect to the loss function. Correct? But testing is not going to be like that. Testing, you want to keep it as it is. We will use the training, we will use the neural network that we have trained to make predictions on a testing set. Then we will compare those predictions with the actual labels. So we are not going to encode it. So this was your train, test, and validation split. So it is not mandatory, okay, that we always do it like this. But since you are not aware, I have explained it. So if you have understood it, it's good. If not, no problem at all. So now that we have data in proper shape, we can take care of augmentation. So are all of you aware with data augmentation or image augmentation?
Yes.
Okay, can anyone tell me why we do augmentation?
That is to generate the data, more data. Um, we skew the images, tilt them left, right.
Okay, are you 100% sure when you say we generate more data? So let's say I'm providing in a batch 1000 images. So, and we apply augmentation on those 1000 images. So is it like more images are going to be generated, or we are going to make a few changes in those existing 1000 images?
We generate more, right? We tilt them left, right, and skew them just that
Yes,
we
we
can have
skew
more
them.
data.
So like
Huh.
we skew the original images and the number of images remains same, or like we skew and add more images.
I think we add more.
Okay. Others?
Yes, yeah, increasing the size from existing image.
Think again. Let me give all of you, because this is very important.
It is being used to generate multiple images from a single image by changing its orientation.
Okay. So let me give all of you 2 minutes to think about it. My question is simple. Let me draw something. Okay, what do we use for augmentation? I hope all of you are aware we use the image data generator, correct?
Correct.
Yes or no?
Yeah.
So this image data generator, and let's say I have performed some operations here. I have the rescale, I have rotation, I have zoom, I have flip. Okay, just like some operations I have used. And I have selected my batch size to be 1000. So I'm providing 1000 images. So my question to all of you is the output that will be there, will it be the same output, a batch of 1000 images, or the output will be like more images? Let's say 4000 images or 5000 images have been, let's say n number of images have been added after augmentation. This is the
Mo-
question.
More
First,
images.
first 1000 as it is, meaning we will perform these operations, a combination of these operations on these images, and then that will be, these images will be the output after augmentation. Second option, no, these images will remain as it is. We will create more images with the help of augmentation, and that will be our output. So select an option. Take 2 minutes to understand this and then answer.
Option 2.
You can search also. You can go back to your notes. You can go back to a neural network you have created where you have done this and see if the number of images were being changed or not. Everybody should answer. What are you referring to, Morris? You are referring to this difference, or you are referring to the concept of augmentation itself?
So this difference and the concept was not like fully taught.
Okay. No problem. Today we are understanding it. It's very important, right? And this confusion is very common. So that's why I have given this task first to all of you. I want all of you to go back to your project and think about it. Yes. Any answers now? First option or second option?
Second option.
Second option.
What's the first option? Because I can't see your, I can't read your writing.
Okay. More answers?
I said, what was the first option? Because I
First option
can't.
is that the number of images remains same.
Yes.
Second option, it adds more images.
Now that I have searched it, I can see it doesn't increase. It's the first option. It just adds, changes the data for every epoch that we run.
Because you have searched it.
Yeah,
What I
yeah.
was referring to with the timing, like you go back to one of your projects, there you see the input and output if there are any changes.
Okay.
Anyways, the correct answer is first option. Okay, all of you pay attention here. Without augmentation, what happens is, let's say your batch size is 1000 images in a single batch. So you provide that those images and their corresponding labels as it is to the neural network for training. When we apply augmentation, then we just have an additional phase. Okay. First, our batch of images passes through the image data generator object, and then we provide it to the neural network. Now let us understand what this does. So in the image data generator, we mentioned some augmentation operations. Okay, let's say we have mentioned some operations. So it is not the case that it will create or add images applying these augmentation. For example, let's say a certain operation has been applied, flip operation. So it's not like 1000 images will be there and then there will be 1000 more images with flipping. No, a random combination of these operations is applied on the original set of images. For example, let's say I have mentioned rotation, zoom, flip. So a random combination of these will be applied on an image, maybe a different combination on another image, a different on another image. So it is augmenting the already existing images. For example, let's make it simple. Let's say let's for understanding, let's say you have a batch of 3 images. So your 3 images were like this. Like let's say in this batch you have one cat image, you have one dog image, okay, and then let's say another cat image. So now what may happen is this is the input. So now in this case, let's say on this particular image, a random combination, let's say a little bit of zoom and a little bit of flipping was applied. So now your cat is flipped. Let's say on this image, a random combination, a little bit of rotation and zoom is applied. Okay. So now your dog is a little bit rotated, something like this. Let's just assume I'm not able to draw it properly. And then on this image, some other combination was applied, but the number of images is going to be same. So this was the input. The augmentation will be performed on these inputs and the images will change obviously, but it's not the case that new images will be added. No, the already available images are getting augmented. So if the batch size is 500, the output will also be 500 after augmentation. If the batch size is 100, the output will also be 100. If the batch size is 1000, output will also be 1000. Clear to all of you?
So it does not increasing the size, right?
No. The image data generator is not increasing the size.
I mean the numbers. I mean to say the numbers, right?
Yeah, absolutely correct. The number of images, correct.
Because what we learn related with the augmentation is it is being used to generate multiple images from a single image.
No, no. When you say generating multiple images from a single image, it means it is increasing the number of
Yeah,
images.
yeah,
No,
that's what my doubt is. Yeah, that's what actually
no,
we
no.
want
It is
to.
not generating multiple images from a single image. It is augmenting the single image to generate a new image, augmented image. For example, here there is a cat which is just in a straight orientation. Now it will be rotated a little bit, maybe it will be zoomed a little bit. So it is the new version of that, augmented version of the same image.
Got it. I mean, it's basically changing the orientation. That's it. Nothing apart from that, right?
I mean, orientation, I have given just an example. It is changing whatever you have mentioned. You
Yeah,
mentioned
yeah.
zoom,
But
rotation,
the
and flip.
image,
That's what it is doing.
yeah,
Correct.
the base image, whatever image, say for example, if we have only one image, right? The number of images is going to be intact one, right? Only we are going
Right.
to change the direction, orientation, whatever, function or, the functionality that we are going to use as per this, right?
Correct.
Okay, okay. Thanks.
Clear to all of you? It is important. Confirm.
So when you say we are applying a random combination of a newly generated image and already existing data, um, instead of we passing the input as it is, we are combining it with the newly augmented data. So just so that we
No,
can
no,
train the
no, no,
model.
no. If you are combining the input with the newly augmented data, it is increasing the image. It's not like that. So you provide 100 images. Now you apply the augmentation on those 100 images. So those 100 images after augmenting is your output. It's not like you are adding them to the data set.
Yeah, but when you apply it to the model, like when you give it in as an input to your model, there you are giving those augmented images as inputs as well, right?
Correct. As well, no, that is the only input we are giving. Okay, let me explain it with an example. Let me think of something. So, what was your name? Who was asking the question?
Vipul.
Vipul. So, let's say Vipul decides to go on a date. Fine, Vipul.
I'm married, but yeah, fine.
Okay. Okay. Let's just assume you are still going. So, one way is that Vipul just goes on the date in his normal attire, no grooming, nothing at all. But one of Vipul's friends suggests that, okay, he needs to do proper grooming, he needs to augment his attire, okay, he needs to wear proper clothes, okay, in a new getup. So maybe he just goes to a place where all of his attire, his hairstyle, and all of the grooming is done, and then he goes on a date. So that is a different. So it's not like we have the Vipul and then we have the augmented Vipul, two people going there. It's the same person who has received this grooming and augmentation who is going there. So that is the difference. So it's not like we are adding new images, it's the same set of images which we have augmented. Now those augmented images are going to be provided to the neural network.
Yeah, so that was my doubt. So if we have augmented the data now, instead of sending all the original data, some original data is being sent and some augmented data is being sent to the model, right?
No, how can we say some original data, some augmented data? How so?
So what I mean,
Because
okay,
augmentation will be performed on every batch.
okay, so only augmented data is being passed now.
Yes.
Oh, okay. Okay, yeah, that was my doubt. Thanks.
Okay. I'm not really able to think of a proper example using which I can explain this. Let me think of something. Just give me a minute. Okay, in order to understand the example, first we need to discuss why we need augmentation. So can anyone answer that first? Why we need to augment our images?
Because for a trained model, always it's not the inputs are same, right? So it might be like a net tilted angle or something else also.
Correct. So let's say we have a data set, and in that data set, we are not sure what type of images we have. Okay, we may have all the images. Let's say we are talking about cats and dogs, so maybe all the cats are looking straight or it is visible completely. Correct. But when we have trained our model, so when we have deployed our model in the actual use case after deployment, we are not sure what kind of inputs it is going to receive. There, the inputs may be in images, may be in any orientation. So our model should be robust towards everything. So let's say if you're talking about cat, so it doesn't matter the orientation of the image, whether the cat is lying down, whether the cat is hanging somewhere, jumping from somewhere, only the side version of the cat is visible, or the front of the cat is visible, correct? Or only a certain, only the face is visible, the tail is not visible. In any way we receive the image, our model should be robust enough or capable enough to detect that, okay, this image is a cat. That is why we perform augmentation. It also helps with overfitting. It makes our model training robust towards uh, all the kinds of images. Okay, all the different ways it can receive a particular image. If you train only on a certain set, for example, if you only train a neural network on cat images, which where the cat is completely visible, it is looking at front and everything is correct. If you have only one type of images, then that's the only thing the neural network will learn to detect. If you are providing an image where the cat is, let's say, not visible completely or has a different angle, different side pose or something, then the neural network will fail to detect. Okay, it will overfit on the just one type of image. That is why, to make sure that our neural network is robust towards all the different aspects of the image it may receive, we perform augmentation. Clear to everybody why we perform augmentation?
Yeah.
Yes.
Okay. So I hope now the idea of augmentation is clear, and also that confusion that why exactly the image number of images remains same. It does not change. Okay, we are
Clear.
augmenting the original set of images and then we are providing it to the neural network. No new images are getting added. But this confusion arises because this image data generator augmentation, and then there is one more concept called data augmentation. Okay, So sometimes it is used to increase the size of data sets also. Let's say you have a less number of images. Let's say I have only 500 images, but for my data set, I need to make them 2000. So then what I may do is I may do some augmentation on my data and then increase the size of my data set. So I create 1500 augmented images, then I concatenate them or add them to my data set. So that kind of augmentation is different. Okay. We are not talking about that. We are talking about the image data generator augmentation that we do before the training. So remember this difference. Now let us perform that. So first of all, we need to perform augmentation, we need to create an object of the image data generator class. So let's call it train data gen. Inside this, we can provide what we want to perform. So rescaling should be done. Now, again, just for the purpose of revision, let me ask the question, why we do this rescaling? What is the purpose? Rescale 1 by 255 means multiply all the ND arrays by 1 by 255, simply meaning divide by 255. So can anyone tell me why we are doing this?
To bring the value
Higher
between
numbers
0
will
and
be
1.
Absolutely correct. To bring all the values between 0 and 1. And why we need to do that?
if there are higher numbers, the training might be just full stop.
Sorry, higher numbers.
The training will be biased, like it will give high priority to the higher numbers.
Correct. So basically the answer is normalization. We do it for normalization. When we have structured data, there are different ways to normalize. But in case of images, we know that all the values are going to be between 0 to 255. Yes or no? Do all of you agree when I say that we are 100% sure that all the values are going to be between 0 to 255?
Yes.
Yes. Okay, let me ask another interesting question. Why? Why all the values will be between 0 to 255? I'm asking these questions just for revision because some of you have already created these projects, so you must learn something new, or a lot of you must at least revise all the concepts. That's why I'm doing it. If I just finish the project, it will make no sense. Why all the images are between 0 to 255? All the values we are using to represent the images in the form of ND array are going to be between 0 to 255.
Because 0 is being used for white, right? And 255 means black, right?
Even in case of RGB. In grayscale, your answer is correct. If you're talking only about grayscale images, your answer is partially correct. But then I can ask a cross question, why? Why 0 is white and why 255 is black? Why this range?
Because it's a matrix, right? Pixel value that's used to consider, right?
So in a matrix, is it the case we can only have values between 0 to 255? I can have any value in a matrix.
Because a pixel lies between 0 to 255, right? Of
Yes,
an image.
okay, you are getting to the point. My question is the same. 0 to 255 are being used to represent the intensities of those pixels.
Correct.
So if I keep it simple, if I talk about black and white images, 0 means absolute white, as white as it can be. 255 means
Black.
no, I think the reverse is there.
0
0
means black.
black, and as black as it can be. 255 means as white as it can be. Two extremes. So why exactly is that range 0 to 255? Why it's not like 0 to 100? Okay, 0 means absolute black and 100 means absolutely white, and in between you have different shades. Why not? Why exactly 0 to 255? Why not 0 to 500? That is the question. First, tell me, are all of you understanding the question? What I'm trying to ask?
Yes.
The question is simple. Why this 0 to 255? What is the reason behind this?
So in maybe
Because it is represented as 8 bits, and in that it ranges from 0 to 255.
Correct. So to represent each pixel, we use 8 bits or simply 1 byte. That's the reason. Let me explain. Did all of you have a session where you understood how images are represented in memory?
Can remember.
Yeah.
Okay. So you see, 1 pixel, 1 byte of memory, meaning 8 bits, meaning 2 raised to power 8 distinct numbers, meaning total 256 numbers. So if we start from 0 to 255, that is the reason behind it. We are using 1 byte of memory to represent 1 pixel. Okay. And 1 byte has 8 bits, and using 8 bits, you can represent total 256 distinct numbers. That is why 0 to 255 is the range. Now making sense?
Yes.
Others?
Just one. I mean, I don't know. 2 to the power 8 is 256, right? Why we haven't considered 256?
No, 0 to 255 are total 256 numbers.
Got it. Got it. Sorry, my bad. Thanks.
Like for example, if I have 2 raised to
Got it.
power,
Got it. Thanks. Yeah, I got it.
okay. Okay, let me, just to keep it interesting, let me tell you something. Have all of you heard those advertisements that, okay, our maybe TV, phone, or some advertisement that our devices can show 16 million colors?
No.
In the past, let's say, whenever you have seen, you are searching for a TV or a smartphone, so for screen, they say, okay, our device can show 16 million colors. I think it is written all over the place. They use this term, they use this number, 16 million colors. No one has seen this?
Yes, in smartphones.
Yes, smartphones, TVs also. You will see it everywhere. Okay, our device can show 16 million colors. So
Today has been changed with 1 billion colors.
yes, 1 billion is also there nowadays. So let me tell you the reason behind both of these. Like actually there are not so many colors, but why they are able to get away with this. So 16 million colors means they are using 8-bit panels. Okay. Now 8-bit panels RGB. Now I hope all of you are aware that if it is grayscale, we need 1 pixel, 1 byte. If it is an RGB pixel, then we have 3: red, green, and blue. So 1 byte for each. So one RGB pixel requires 3 byte. Yes or no? One for red, one for green, one for blue. So when we say 8-bit color panel, okay, 8-bit, not black and white, 8-bit color panel. So they have uh, 8 bits for each: red, green, and blue. I hope all of you know all the colors on screen are produced by a combination of these. So 256 different shades of red, 256 different shades of green, and 256 different shades of blue. So if you combine like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 2, 2, just like that, there are total these many combinations. So can anyone tell me what is this number? Calculate and tell me what is this number.
167.
77216.
So basically almost 16 million. Yes or no? 1, 2, 3, 4, 5, 6. So that is the reason why they advertise like this. So it's not the case that you have so many colors. No. If you combine these shades of red, green, and blue, so let's say 20, 0 to 20 of this, 0 to 20 of this, 0 to 20 of this, they all are going to look exactly the same color to you. Maybe when you have 50 of this, 50 of this, and 50 of this combination, then you will see a difference from 0, 0, 0. That's how it is. But they are able to advertise. What is the science behind saying 1 billion colors? Okay, now they are using 10-bit panels. In 10-bit panels to store pixel information, you are using 10 bits. Now 2 raised to power 10 is 1024. How much is it? Is it 512 or 1024?
1024.
1024. So now how many combinations of those pixel values you can have? 1024 by 1024 by 1024. Now, can anyone tell me what is this number?
1073 741824.
So 9. So almost 1 billion. So this is the reason behind a 1 billion colors display. Okay, so maybe now you will never get fooled by this. A lot of people actually do. Nowadays, all the panels are 8-bit. I mean, the normally available ones, all the panels are 8-bit panels. So it doesn't matter whether someone says it or not, they are all capable of showing. It's like 16 million patterns of these values. It's not like 16 million different colors. Most of these are going to look same, exact same. So 10-bit panel, they are obviously a little bit more expensive because they have more color information. It is in cameras also. I mean, those who use the cameras, if anyone has ever used a camera or purchased a camera, look for specifications. You may have seen something like 8-bit video or in 10-bit video. Yes or no? Like you may have heard that
Yes.
10-bit video is better for color grading. Why? Because there you have more data available, more information available for each pixel. It looks like it, okay, 8-bit or 10 bits, there's a difference of only 2 bits. It's not a difference of only 2 bits. See the numbers. Using 8 bits, you can have only 256 different values. Using 10 bits, you can have 1024 different values. So 10-bit actually has, whether 10-bit image or 10-bit video actually has 4 times more information than an 8-bit video. A 10-bit panel will be able to show better contrast or separation between colors 4 times than an 8-bit panel, which is huge. So it's like that. It's not related to neural network or something, just some interesting information. Yes, Ifi, you have raised the hand.
Yes, please, can you help explain this concept of raising it to power 8? I'm still not clear with this 2 raised to power 8 and the 2 raised to power 10.
You mean the 16 million, 1 billion difference or
No,
this one?
This, yeah.
This, okay. So this is about bits, right? So are you available with, are you aware with the concept of bits and bytes?
Yes.
What is a byte? What is a bit? So when we say 1 bit, so 1 bit can only show 2 distinct values, 0 and 1. 2 bits can show 4 distinct values. How? 0, 0, 0, 1, 1, 0, 1, 1. So this you can say is 0, this is 1, this is 2, this is 3. So 2 bits can show information from 0 to 3. Correct? 3 bits can show 0 to 7, total 8, 2 raised to power 3. So the number of distinct values uh, that can be shown using n number of bits is 2 raised to power n. So if I have 1 bit, 2 raised to power 1, 2. 2 bits, 2 raised to power 2, 4. 3 bits, 8. So just like if I have 8 bits, so 8 bits are capable of representing 2 raised to power 8, total 256 distinct values.
Okay.
And those 256 distinct values, as we start from 0, they are 0 to 255.
Thank you.
Okay, so this is what we use to represent a pixel. 0, in any case, if it is being used for black and white or for red, green, blue, 0 means the lightest one possible. So When we talk about brightness or white, 0 means absolute black, 255 white. Okay. 0 of red means the lightest red, and 255 of red means the darkest red. I mean, the most red as it can be. I hope it makes sense. That is what these values are used to represent.
Thank you.
Okay, let's continue with the augmentation. Let me just write everything so that you know what are the mostly. I will keep the ranges short so that they do not have much of an effect, but you will have an idea. Okay, these are the most commonly used augmentation parameters that we have. So these are some of the most common. You see, there are so many. It's good that it has opened. You can clearly see there are so many augmentations, right? But these are what I have mentioned here. These are the most commonly used ones. So after we have created this object, we need to fit it on our training set, because this one I'm creating is for training set. Done. Now we need to create a generator object, which we will mention in the during the time of training. Done. So let me once again explain what will happen. One way is that I do not use the augmentation in my neural network while training. Okay, that model.run function. I just mention x train, I mention y train, and I mention batch size is equals to 400. Now, what will happen there is you will take 400 images and labels, and you will provide them as it is to your neural network. So take a batch of 400 images and their corresponding 400 labels and provide that to your neural network. But what we will do is now, instead of mentioning this in the neural network, we will mention the train generator. So what this train generator will do is, this train generator is basically an object of the train data gen, which is an object of the image data generator class. So what this is going to do is take a batch of 400 images and their corresponding labels. Labels are not changed, obviously. Apply augmentation as per the parameters mentioned in the train data gen object. Okay. Take 400 images and 400 labels from here. Apply the augmentation. Flow means take here and flow from here and provide it to that. This object will perform the augmentation based on the given parameters, and it will give 400 augmented images and 400 corresponding labels. Now, this is what is going to be provided to the neural network as input. That is the difference. How augmentation will be done? Now, what do these parameters mean? It means that a random combination, you see, all of them are ranges. It's not like whenever we do rotation, 20% rotation or 0.2 is going to be done. Whenever we do zoom, 0.1 is going to be done. No, these are ranges. Any random combination of these can be applied on any image. Like for on a particular image, rotation of 10% and zoom of 5%, with shift of 2%, and 0.1 means 10%. I hope you understand, in that particular range. So height shift of, let's say, 3% can be applied. Somewhere vertical flip may be applied, somewhere it may not be applied. Somewhere only zoom and rotation may be applied, somewhere only height and shear may be applied, right? So a random combination of these is applied on each image to perform the augmentation. Now you may ask, why random? Because we want our images to be different in all the orientations. Yes, Ifi.
So the figure 0.2 are the maximum values.
Sorry, 0.2 are
The figures attached to the ranges, like rotation range is 0.2. So is 0.2 the maximum value, or is that the 20% you
correct,
will
the
take?
maximum value. Yes, it's a range from 0 to 0.2. 0.2 also indicates like 20%. Right? So yes, absolutely correct. It is a maximum value. Any degree of rotation can be applied from 0 to 20%. It can be 5, it can be 2, it can be 10, it can be 15% rotation, anything.
Okay. Yeah, please, can you also share the codes?
Yes.
Okay,
So
thank
after
you.
this, how augmentation is done and what is the difference when we apply augmentation and when we don't? Is it clear to everybody?
Just one thing, if we talk about rotation, right? Rotation range, which is 0.2, which is 20%, right? So does it mean we cannot rotate more than 20?
No, it will be based on what you mention. Let's say I
Okay,
mentioned
okay, okay, got
0.4.
got it,
So
got it. Defining
it
the
can
range as
be
per our requirement. So
right,
got it.
right.
But the maximum value will be like 1, right?
Yes. But it also takes values in the form of 10, 20, 30. So it understands that. You can mention the ratios also, or you can mention directly, let's say 20. So it will understand. Okay. Now we need to create a generator object for validation set also. So a question to all of you, do we perform augmentation on validation set or not?
Yes.
Yes.
No. Why would we like to change our set which we are using to judge the performance? Making sense? Training set is being used to train the model, okay, used to update the weight. So we want it to be robust. But the set we are using to judge the performance of the model, we do not like change it or play around with that. Clear? But rescaling is obviously needed, but we do not perform any augmentation. Okay, so here we have performed the generator. We have created the generator objects. Now our next step is to create our architecture, which is where we will learn. Till now we were doing the steps we have already done. We were simply revising. Now we will see how exactly we can use an already existing network. Before doing that, I would like to ask all of you, is everything that we have done till now clear to you? Any doubts till now?
Yes.
Okay. So now I would like all of you to open keras.applications. Okay, just type keras applications or keras.applications. I think it will appear as the first page. So here is our keras.applications documentation. Okay, this is basically an API. Okay, or I mean simply a library, you can understand like that, where all the models that you can use are available. So all of these models you see, exception VGG 16, VGG 19, different versions of ResNets, different versions of Inception, mobile net. Okay, it's not like all of them are very different. There are mainly 5 of them. You have VGG networks, you have residual networks, you have Inception networks. Okay, you have efficient net, and you have mobile nets. So these are different ones, and then others are just different versions of these. So what are these? These are the neural networks that are already available, very huge architectures that you can use as it is to solve your problems. Can all of you see this website? Yes?
Yeah.
Yes.
Okay. So how do you know which how to use a particular network? So today we are going to use VG19. I'm going to show you the code for that. But it is for the everything is same. For the code for everything is same. You use VGG19, you simply have to write keras.applications.vgg19. You want to use ResNet 50, you just write keras.applications.resnet 50. It's like that. So let's go to VGG19, and we need to understand that. So all these parameters we need to understand, or not all of them, only some of them, and they are same for every neural network that you want to use. So first one is include top. Now you can read more about them here. I will explain quickly. So whenever we are talking about drawing the neural network architectures, like on paper, we always represent them like bottom to top. For me, that means your input layer is, when you're drawing the architecture, input layer is going to be here, and then your output layer is going to be here. So when we say include top, we are referring to the fully connected layer part. I hope all of you are aware, in a convolution neural network, we have the convolution part and the fully connected network part. Yes or no?
Yeah.
Okay, let me again, just for the sake of revision, ask this question. Why do we have both? I mean, if we know that CNNs are better at tasks related to images, so why we are still using the fully connected part? Why don't we just use convolution layers and pooling layers? Why we still need the fully connected layers?
We can do feature extraction using pooling and stuff, but still for classification we would need fully connected layers, right?
Correct. Absolutely correct answer. So the use case of convolution layers or pooling layers, basically the convolutional network part, is to extract important features. But when we are doing classification, what we need in the end, we need a probability vector using which we can determine that, okay, if this is the final class, this is the final class. So the convolution neural network does not produce a probability vector. It will produce the features it has extracted. So we still need those fully connected layers which can take those important features and can finally produce a probability vector which we can use to perform classification. Right? So I hope that is clear. So here, when we draw the architectures of these neural networks, we draw the architecture in bottom-up manner. That means input layer here and output layer here. So CNN part, fully connected network part, right? So include top parameter refers to whether you want to include the fully connected part or not. If you say true, you will keep the fully connected part. If you say false, you will avoid the fully connected part and only take the CNN part. That's what this parameter means. So we do this if your problem is exactly same, because fully connected part is dependent on the input and output. CNN part is not. So it can be reused even if the problem is different. So let's say the problem is same. All of these neural networks are trained on ImageNet dataset, which has 224 by 224 by 3. Okay, input, and 1000 classes are there. You can read more about that dataset in this paper. So if you are also dealing with a similar problem where you have this as the input shape and 1000 as the output or total number of classes, then you can also keep the fully connected part. If that is not the case, then you can remove the fully connected part just by saying include top false, only keep the CNN part, add your own fully connected part to customize the network as per your problem. Second parameter, weights. So this one, you can mention what kind of weights you want to use. So ImageNet weights, instead of setting random weights, you can always start with ImageNet weights, even if you are training and customizing it, because they serve as a good starting point. Input tensor, you can ignore. Input shape. So if you are saying include top equals to false, right, then you need to provide input shape, because now you need to provide your own shape. Pooling and classes, they also always remain the same if you are setting the include top to true. If you're setting it to false, then you are not required to provide them, because the number of classes will depend on the fully connected part you are adding, and then this one also will depend on what you are adding. So whenever you are using an already available network, what you need to take care of just three things: include top, input tensor, sorry, input shape, and weight. Just three things: one, two, three. When I create the network, then I will explain more about them. Other parameters, I think all of you can read from this web page. I will only talk about these three important ones. Any neural network architecture you need to use, just mention these three things. Now, let us understand this better from our notebook, where I will also be able to show you the architecture. Okay. So let's say I have decided to use the VGG 19 architecture. So that is what I need to write: tf.keras.applications.vgg19. This keras.applications is basically the same what I showed you, the documentation for this API. Inside this function, we just need to take care of three things. Although it will show you everything, but you need to take care of three things: include top, and first writing them with their default values. Let me keep this empty for now. None meaning it will take the original shape for ImageNet dataset. Okay. So let's talk about the first use case. First use case is that your problem is exactly same as this neural network was trained for. Like just like the ImageNet dataset, it has 224 by 224 by 3 input, it has 1000 output. So your problem is exactly same. In that case, you can load this model as it is without changing anything. Okay, these are default values. So even if you just write a bracket here and then import it, it will work. But I'm writing them here for your reference. Then you can use this model as it is without even training. Let's have a look at the architecture of this model. No need to change anything. Here is the architecture of this model. It has a convolution layer, then again a convolution layer, then a pooling layer, then two convolution layers, pooling layer, then four convolution layers, then a pooling layer, again four convolution layers and a pooling layer, then again four convolution layers and a pooling layer. You can see. So it basically has 5 blocks for the convolution part. First block has two convolution layers and a pooling layer. Second block, two convolution layers and a pooling layer. Third block, four convolution layers and pooling layer, and fourth and fifth are also the same. Now, what are these blocks? These blocks are known as VGG blocks. You don't need to understand it. I'm just giving you an overview. So what is a VGG block? In a VGG block, you basically have multiple convolution layers before a pooling layer, and the number of filters and the shape remains same in a certain block. Okay. When we set, if you remember padding, when we say padding is equals to same, even after convolution operation, the shape is maintained. So you can see here, all of them are using 256 filters and the shape is also maintained. That's a VGG block. So I was explaining, if your problem is exactly same, you can use this neural network as it is. But let's say your problem is different. Okay, as per our problem, our input is actually 32 by 32 by 3 and I have only 10 output classes. Then what we can do is we can only include the convolution part, and we can say the include top to false. Now pay attention. When we print the summary, when we create a neural network, this appears at the bottom. But when we are drawing architectures, we draw them in bottom to top manner. So that's why it is saying include top. And by include top, it simply refers to this part. Okay. Just to avoid the confusion, that's why we say it is top, whether it is at the bottom. So when we say currently it is showing the fully connected part, but when we say include top equals to false, then see what happens. Now you can see the fully connected part is not there. You have only received the convolutional part. Yes or no?
Yeah. Yes.
Okay, great. And now you also see it is showing none. Let me show you again. When it was true, it was taking the weights and everything according to the original network. So 224 by 224 by 3 was the input. You can see here. But when I am saying include top equals to false, that means I want to customize this neural network. And that also means, okay, I am supposed to provide my own input shape because now it is not the original one. So now you see it says none. So let us provide our own shape. Our shape is 32 by 32 by 3. Done. That's it. So when it doesn't matter which neural network we are using, you just need to change these two things in order to use it. What we will do after this, we will add our own, after this network, we will add some fully connected layers where we can control what is going to be the output and what is going to be the activation function. But before that, let me show you some others also. This is VGG 19. So when you look at VGG 19, most of you may be thinking that, sir, there is nothing tricky or sophisticated about this network. We can also create something like this after 2 or 3 trials. Yes or no? Do all of you agree with this?
Yes. Yes.
Okay. So with VGG it is true, but let me show you a different one. Residual networks have the concept of residual blocks where the inputs after every 2 layers is provided as output again after the combination to avoid problems such as exploding gradients or diminishing gradients. Inception nets make the network wider. Like for the same input, they will have different paths. Okay, like 3 by 3 filters also, 5 by 5 filters also, 1 by 1 filters also. But we are not discussing that. Let me show you what the inception network looks like. Here, so this is the one. So maybe all of you can create VGG 19, but can all of you think about creating a neural network like this now? Maybe after a lot of experience you can, but what about now? Can we think of creating something like this? Yes or no?
No.
No.
Right? So that is where these already available architectures help us. And this was created not like in a day, but a lot of years of research, a lot of data sets, and then it was created, but now it is available for us to be used as it is. This is the benefit. There are even more larger ones. If I show you Inception ResNet Volume 3, there is something like that. It is even more bigger. So we can use these. For this problem, we are going to use VGG 19. Maybe you can try with other ones. Include top, we are going to say false because our data set is a bit different. And input shape, we are going to set 32 by 32 by 3. And in this, we are going to add our own fully connected layers. I hope all of you were able to see the differences. If you are using the network as it is, keep everything same. Include top true, input shape none. Okay. If you want to customize it, say include top false and provide your own input shape. And here you just have to mention the name of the network you are using. That is the only difference. Can all of you see the summary? Okay, so it is almost a time. So let us start the part where we customize it to solve our own problem. Basically, we add a few fully connected layers tomorrow. Let me keep the last 5 to 6 minutes for doubts. Yes, Ifi.
Please, I just need a clarification of the concept behind the output shape. I'm still a bit confused. I know the input layer, we have the number of inputs, the none, the width and the height, and the number three, which is the RGB. But when it gets to the block, I have number of filters 64. Then you get to the second one, you have 128. I am confused with the numbers, how they are varied. Is there any particular way?
Yes. So I hope you're aware that the convolution operation, basically the output of a filter, is always 2D. Like irrespective whether your input is 32 by 32 by 1 or 32 by 32 by 3, if you are applying convolution operation, its output is going to be 2D. Yes or no?
No.
Okay, all of you have learned convolutional neural networks.
Yes.
So when you are performing a convolution operation, irrespective of whether the input is RGB or grayscale, the output is always 2D. That means it is going to be grayscale because we are only talking about patterns. So the 32 by 32 here represents the output of a single convolution operation. And you must be wondering, sir, how exactly is it 32 by 32? If like, why is it not reduced because of convolution? Because here we keep the padding same. That's why the resolution is maintained. So this 64 here is because we are using 64 filters. The third
Yes.
value you see in the output of a convolution operation, it indicates the number of filters being used. One filter will produce 32 by 32. You are using 64 filters, so you are producing 32 by 32 by 64. In this block, you are using 128 filters. So it is 128, 28. In this block, you are using 256 filters. It is like that. Clear?
Can you little bit explain about what is block one, con one, block one, con two? Yes.
This is the architecture of the VGG network. The VGG network uses a VGG block structure. What happens in a VGG block is two things. In a VGG network, you are using VGG blocks. In a residual network, ResNet, you use residual blocks. In an inception neural network, it doesn't matter any version, you use inception blocks. So all of these concepts are there, which you can study in detail. Okay, so we just combine a lot of these blocks to create the overall neural network. What is VGG blocks? So VGG blocks have mainly two properties. What are those? So they use multiple convolution layers. Okay, let's say n number of convolution layers before a padding layer. First concept. Second one, that the shape remains same throughout a block and the number of filters also remains same throughout the block. Now, what we use to keep the output shape same after convolution operation? Padding. Yes or no? If I set the padding parameter to same, then what will happen? The general decrease in the resolution that happens after convolution operation, that will not happen. So in a VGG block, these are the properties that are followed. The output shapes remain same because we are using padding, and the number of filters remains same. So if you look at this block here, you have 64 filters in both the convolution layers, and the shape is also not changing because padding is same. In this block you have 128 filters, shape is same. In this block you have 256 filters, the shape is same. These are our VGG blocks. Clear? It's
Yeah.
just a way to design and create the architecture. Your doubt
Thanks.
also clear, Iffy, that on what does this number depend? 64, 128. It is the number of filters.
I know it's a number of filters, but I don't know how. Okay, you just said it's because it's from tribute architecture.
Yeah, that is how, if you're asking why is it exactly 64, so that is what, that is how the architecture is designed. They tried
Okay.
multiple things, they did a lot of research, and they found, okay, this is working well. So this is the architecture itself. It's not like we are creating it. This is how the architecture exists.
Okay. Thank you.
Although all of you can study it in detail, but let me give you an overview. What are residual blocks? So let's say you have one block, you have two blocks, and what is going to happen? The input that this block received will also be combined with the output of this one, and that will be the input for the next block. We call them skip connections for residual blocks. So you have the concept of skip connections for residual blocks if anyone wants to study further, although not mandatory, but you can. So we use residual blocks with skip connections. Okay. Then your inception blocks have this concept of, instead of making the neural network longer, we can make it wider. So let's say for each input, there are multiple paths. Okay, 3 by 3 filters are also being used, 5 by 5 are also being used, 1 by 1 are also being used. Then combine their outputs, then this is the input for the next block. Again, the same. So here we have residual blocks and here we have inception blocks. Residual blocks have skip connections. Inception blocks have multiple paths. These are the basic concepts in case anyone wants to study further about these networks. Any more doubts?
Out of those all models, how can we choose choose our
Always start with the simplest one like VGG, then try inception, resonate, then try inception. So these three are the best performing ones. Just like in machine learning projects, before deciding the final one, you tried multiple models. Okay, if it is a, let's say, regression task, then try the linear regression. Okay, let's try the k-nearest neighbors regression. Or let's try, in the end, let's try the XGBoost regression because that is definitely supposed to perform well. It is the most complex and time consuming process. So similarly here, you try simpler ones first. Okay, then move on to complicated ones to see which one works best. Okay. So was this revision session helpful? Revision plus project session? It is not completed yet. We will continue tomorrow.
Yeah, very good one.
Okay. So tomorrow, I think within 15 to 20 minutes, we will complete this project. Now I'm thinking what else we can do tomorrow. So have all of you used OpenCV library?
No.
No?
No.
Everybody needs to give me a response. So tomorrow
No.
I will introduce you to that OpenCV library. Okay, we will create an interesting project related to face detection.
Sir, to read more on this, I mean, these models and like how they are different and the architecture and stuff. Is there any material or directly from the website?
I mean, if you search, there may be articles also. You can find a lot of articles. It's not mandatory reading their architectures. You see, their architectures are complicated.
Yeah.
You can understand basics, like I told you. All you need to know is ResNet, what is residual blocks, what is inception block, because their architecture understanding it will take a lot of time.
And
Let me show you.
okay,
Let's say we talk about this architecture of inception. Where is it? So obviously it is going to be a little bit tricky for you to understand all of these details and maths. So I'm not suggesting that you do. All you need to know is just, you see, this is what I was drawing. Like, what is a residual block? What is an inception block? That will be more than sufficient.
yes, sir.
Basic understanding.
Yes, sir. And agreed. But from my interview standpoint for this entire thing, I mean, like deep
No,
learning on the
nobody
whole.
asked these entire things. You need to know how to use them. You don't need to know their architecture in detail.
Okay. I'm asking like for generally deep learning, like is there anything like a good source we can refer for interview for the question? Because these questions, if you ask, like really like making us
Yes, what I asked, those were general things. I mean, you need to know them obviously, like loss function, what loss functions are available, which one you use in which case, how does loss function changes the output shape, softmax, okay, what is the input softmax receives, activation function, what is the output softmax provides. I mean, these things are general purpose, so these you need to know. But we are talking about transfer learning architectures, that is a little bit out of scope. You don't need to go into the details there. But the
okay.
questions that I asked today, those obviously are a must. You need
Okay.
to know them.
Yes, sir.
If
Got it.
someone asks you that what is the difference between categorical cross entropy and sparse categorical cross entropy, you must know. When do we use softmax? When we use sigmoid, you must know. Someone wants to know, okay, explain how the softmax function works. You need to know that. How a convolutional neural network works, how is it different from an ANN? How is the convolution layer dependent on the, how is a convolution layer not dependent on the inputs, but the weights inside a fully connected layer are dependent on inputs. Like these things, obviously, you need to know.
Yes, I got it. Thank you.